Hello students, Ms. Slyman here. So we talked before about how to determine graphically if an expression is one-to-one, and that's when we use the horizontal line test. Well, algebraically, let's think about how to do it that way. So going back to the definition of being one-to-one, if I think of some random points for my function, so x, f of x. If it's one-to-one, then if I put in a, I'll get out f of a. If I put in b, I'll get out f of b. And if it's one-to-one, then if a is equal to b, then f of a has to be equal to f of b. Because for each x value, I can get only one y value. So if these two things were to be the same, then a would have to be the same as b for a one-to-one. So let's write that down. So algebraically, one-to-one means for a equal to b, f of a has to equal f of b. And vice versa, that goes both ways. So if f of a is equal to f of b, then a must be equal to b. So let's look at this expression. If we put in an f of a, we would have a cubed minus a, and then b cubed minus b. And this would have to be true for a equals to b only. Otherwise, if this is also true for some a not equal to b, then our function cannot be one-to-one. So let's look at what happens here. I'm going to put together the cubic terms, and I'm going to put together the linear terms. Notice this factors. Maybe you remember factoring a difference of cubes. It's going to be a minus b times a squared plus ab plus b squared. I know this from years of experience. It's not something you need to have memorized. That would be equal to a minus b also. Now I notice that these two are the same thing. So if I divided both sides by a minus b, I would get a squared plus ab plus b squared equals 1. And because I've just divided by a minus b, I would have to say that a cannot be equal to b. Well, if a can't be equal to b, then any other term that this is true for would mean that I'm not satisfying this condition that a has to be equal to b. Yeah, so already here I can justify that it's not one-to-one. Another way we could have done this is to set it equal to 0. So if I set it equal to 0, I would have a minus b times a squared plus ab plus b squared minus a minus b equals 0. I could factor out the a minus b and be left with a squared plus ab plus b squared, whoops, minus 1 equals 0. Well, this would have a solution when a equals b. That's what I want. But this is also going to have a solution where a does not equal b. So let's look at that. That would mean a squared plus ab plus b squared minus 1 would be equal to 0. A squared plus, I'm going to be left with this again, a squared plus ab plus b squared equals 1 when I move that minus 1 over. So I'm just going to work over here. Well, looking at this, I can already see a pair just by inspection that if a was equal to 1 and b was equal to -1, this would be true. So obviously 1 does not equal -1. That means that this expression can't be one-to-one because there's more combinations than just a equals b that will give us two y values equal to each other. Yeah? So really what we're saying is that f of 1 would be equal to f of -1. So I have two of the same y values for different x values. So it is not one-to-one. And now let's look at that graphically, just to show as well. So let's open a new window. All right. So if we go into Desmos, we can see that if my f of x is equal to x cubed minus x, I can see straight away, here's my 1, negative 1, so both of those points have the same y value, but I have many points. 0, 0 also has the same y value. So we've got a failure of the horizontal line test, so graphically we can also show it's not one-to-one. Algebraically, by showing that this is true for some a not equal to b, also means not one-to-one.